When two galaxies collide, it looks like cosmic destruction, but the truth is far stranger. Stars rarely crash, yet entire worlds are thrown into chaos. We'll uncover what really happens when galaxies meet in deep space. If you enjoy these cosmic journeys, please subscribe and share. Thank you for watching. Now let's begin. A galaxy is a bound system that holds together under gravity and stretches across distances measured in light travelling for many thousands to many hundreds of thousands of years. It contains stars at many stages of life, clouds of gas in warm and cold phases, fine dust that softens and scatters light, and an extended halo of invisible mass that astronomers call dark matter. Each component moves in response to the combined pull of all other components, so the whole system acts as a single structure. Seen as a whole, a galaxy is not a solid object, but a stable arrangement of many parts that keep their order, because gravity is steady and long-reaching. The bright body of a spiral galaxy is a disk that is thin compared to its diameter. In that disk, stars trace nearly circular paths around the centre, while lanes of denser gas mark out the arms. These arms are not solid objects. They are patterns where gas compresses and then eases as it orbits, so material flows through the pattern, while the pattern itself persists. The central region often swells into a bulge where orbits tilt and crisscross. Around disk and bulge lies the halo, a broad sphere that holds old star-star clusters, and a much larger volume of dark matter that determines most of the gravitational pull. Elliptical galaxies take a different form. Instead of thin disks, they resemble rounded clouds of stars with little cool gas. The stars move on many kinds of orbits, and the combined motions create a smooth light distribution with few sharp features. Irregular galaxies show less symmetry and can be rich in gas and young stars. Dwarf galaxies, which are far smaller, also carry dark matter halos and can be numerous around larger hosts. Differences in shape reflect formation histories and environments, yet in every case gravity ties the parts together across great distances. Inside a galaxy, the interstellar medium is the gas and dust between stars. It includes cold molecular clouds where hydrogen binds into molecules and stars can form warmer diffuse gas that fills large volumes, and hot gas heated by energetic events. Dust grains made of elements such as carbon and silicon absorb blue light more strongly than red, so some regions appear reddened. When gas becomes ionized, it glows at specific colors set by the physics of atoms, and these signals help map motions and densities. Over time, stars enrich the gas with heavier elements, and that enrichment changes how clouds cool and how new stars form. A large spiral typically contains many hundreds of billions of stars, yet they are not crowded. The average spacing between stars in a disk is measured in light years. A light year is the distance that light travels in 1 year and is useful for galactic scales. Because the spacing is so wide, stars seldom collide even when galaxies pass through one another. Emptiness between stars is real at the scale of stellar systems, even though the galaxy as a whole is richly structured. At the heart of most large galaxies sits a supermassive black hole, a compact object with a mass of millions to billions of times the mass of the Sun. It governs the innermost orbits and can power a bright nucleus when gas spirals inward and heats up. In quiet phases it stays dark except for the motions it demands from nearby stars and gas. Compared to the whole galaxy, the black hole is small. Its direct reach is tiny on galactic scales, but over long spans it can grow as inflowing gas and stars feed it. The structure of a galaxy reflects a long past. Gas collapsed within a dark matter halo, cooled and settled into a disk. Stars formed, lived and returned part of their mass to the gas through winds and supernova explosions. Spiral patterns kept appearing in the rotating disk. Satellite dwarfs fell inward and left streams of stars in the halo. Quiet accretion added fresh gas from beyond the visible edge. These processes continue at a measured pace, so day by day, the galaxy changes only slowly, while energy and matter cycle among stars, gas and dust. When astronomers describe the size of a galaxy, they may refer to the radius of the bright stellar disk, or to the region where stars are most common. for a large spiral that radius reaches tens of thousands of light years. The faint stellar halo and the dark matter halo extend far beyond to hundreds of thousands of light years or more. The mass of the dark component outweighs the luminous component by several times, so most of the gravitational pull comes from what cannot be seen directly. Rotation curves, which trace how orbital speed changes with distance from the centre, reveal that hidden mass by showing speeds that remain high, far from the bright disk. Galaxies seldom exist in isolation. They gather in groups and clusters bound by their combined gravity. The space between them, called the intergalactic medium, contains thin gas and traces of heavy elements. Filaments of matter connect galaxies across great distances and form a web-like pattern on the larger scales. Within a small group, relative speeds are modest compared to those in a rich cluster, so gentle approaches and prolonged interactions are common. Tides from neighbouring masses slowly pull on the outer parts, loosening gas and stars and shaping faint streams. Over long times, minor mergers add to the halo and thicken the disk. A single galaxy, therefore, is a changing ensemble of many parts linked by gravity. Stars orbit in the potential well set by all mass. Inside gas flows along patterns set by rotation and pressure, dust drifts and settles, and dark matter provides the deep background pull. Orbit shift patterns move and the whole structure breathes slowly as gas cools and heats. The scale is large, but the rules are simple. Gravity draws, pressure resists, radiation warms and pushes, and time allows small changes to build. With these rules in mind, one can hold a steady picture of a galaxy in isolation, a thin disk or a rounded cloud, a central concentration of mass, extended halos of faint stars and dark matter, and a cycling medium that feeds and receives matter from stars. This baseline picture prepares the mind to consider what follows when another such system draws near. The approach is not a sudden crash. It is a long exchange of force between extended halos, disks, and bulges. Before that exchange begins, it helps to keep in view the essential features just described: sizes, contents, and quiet motions. From that foundation, later changes appear not as abrupt disruptions, but as steady outcomes of the same rules acting across a larger shared field of gravity. Gravity is the steady rule that links matter across distance and gives galaxies their paths. It is an attractive force that pulls any two masses toward one another, and its strength becomes weaker as the distance between them grows. In simple terms, the pull falls with the square of the distance, so a separation that is twice as large brings 1/4 of the pull. On galactic scales, this rule dominates because other forces fade with distance, or require electric charge, which large balanced systems do not carry in net. A galaxy moves as though all of its mass were gathered at its centre, as long as the distance to another mass is large compared with its own size. When two extended systems draw closer, each no longer feels the other as a single point. The near side of each galaxy feels a slightly stronger pull than the far side, and this difference across the structure is what astronomers call tidal force. Tidal force is a gradient, which means it measures how fast gravity changes from one place to the next. Because a galaxy is wide with stars and gas spread over many tens of thousands of light years, small fractional differences add up to gentle stretches that are important over long times. Motion under gravity follows two ideas that are simple to state. Energy is conserved unless work is done by outside forces, and angular momentum, which is the measure of rotation, in an orbit stays constant unless a torque acts. For two bodies that only pull on each other by gravity, the total energy and total angular momentum set the shape of the relative path. If the energy is negative, the path is bound and closed and the two masses orbit their common centre. If the energy is positive, the path is unbound, and the masses swing by once and then part. The common centre of rotation is called the centre of mass or barycenter, and for unequal partners it lies closer to the heavier galaxy. When two large galaxies in the same small group move with moderate speeds, their energy with respect to one another is often negative, so a bound approach is likely. As the distance shrinks, the mutual pull grows, the orbital period shortens, and the relative path can be described by a slowly shrinking ellipse. The point of closest approach is called pericentre. The point of farthest distance is called a post-centre. In a pure two-body problem without any other influences, the ellipse would repeat forever. Real galaxies are not simple points in empty space, so other effects gently drain orbital energy and angular momentum. One of these effects is called dynamical friction. It is not ordinary friction with contact and heat. It is a gravitational wake that forms behind a moving mass as it travels through a sea of stars and dark matter. The wake pulls backward on the mover, taking a tiny share of its momentum and giving it to the many lighter particles. Over many orbits, this effect removes energy from the large-scale motion and helps the two centers drift inward. Tidal forces act at the same time. Because the near sides of the galaxies feel stronger, pull stars and gas are nudged onto slightly new paths. The changes are small for any one pass, but they accumulate. In the outer parts, where the pull from the home galaxy is weaker, even a small extra tug can lift material into swept-back arcs that trail or lead the main disks. The radius inside which material remains bound to its own galaxy against the pull of the other is sometimes called a tidal radius. Material outside that effective radius is more easily stripped and can form long streams. Inside the disks, orbits are nudged away from perfect circles into gently oval paths. These changed orbits can set up patterns that look like bars or bridges when viewed in starlight. The invisible halos of dark matter take part in these same processes. Each halo is a broad well of gravity that extends far beyond the bright disk. When halos interpenetrate their combined potential, well becomes deeper and the location of its center shifts. Stars and gas respond to the new shape of the well by adjusting their orbits over long times. Because the halo contains most of the mass, it controls the large-scale pull, while the luminous parts trace the adjustments we can see. The intergalactic gas between the galaxies is thin, so ordinary drag forces are weak. Pressure from this gas does not stop two large halos from moving together. Gravity remains the organizer. Gravity also communicates timing. The free fall time is the span a test particle would take to fall to the center of a mass distribution if it started at rest. On group scales, this time can be measured in hundreds of millions of years, although long by human clocks such a time is modest for galaxies. Because the free-fall time depends on density, the inner parts respond more quickly than the outskirts. This difference means that deformations begin near the centers and then spread outward as the encounter proceeds. When two galaxies approach one another, there is no need for a direct clash between stars for gravity to change the system. Stars follow the evolving potential and keep nearly collisionless order. Gas, which feels pressure as well as gravity, will have its own responses, but the broad outline is still set by the gravitational field. Even the supermassive black holes at the centers simply follow the same rules, moving as compact masses within the joint potential well, until special conditions bring them closer together. To picture the full arrangement, it helps to hold a simple image in mind. There are two extended wells of gravity, each centered on its own galaxy, and they move toward each other within a larger frame set by their group. As they near the wells overlap and the combined shape dictates every motion. Angular momentum keeps the motion from being a straight plunge so the path curves. Dynamical friction and the transfer of orbital energy to many small motions inside the halos cause the path to shrink. Tidal gradients gently stretch the luminous parts into long faint features that trace the flow of matter through the changing field. Every change that follows in later stages is an expression of these same rules acting over more overlap and over longer times. The approach begins as a subtle change in the background pull that each galaxy feels beyond its own visible edge. At first, the change is small. The far halo senses a slightly stronger tug in one direction than in the opposite one, and the net effect is a slow drift of the whole system within its group. Inside each galaxy, the disk keeps its steady rotation, and the bulge continues to glow with the smooth light of many overlapping stellar paths. In the halo, old star clusters mark long orbits that now lean a little toward the oncoming mass. These delicate tilts are quiet signs that the large-scale field of gravity is no longer symmetric. The two disks do not usually face each other with perfect alignment. One may tilt relative to the other by an angle that can be small or large, and the lines where the planes would meet define a simple frame for the encounter. Because of this geometry, one outer disk begins to rise and the other begins to dip when measured against an imagined midplane that once looked even. The result is a faint warp. The warp is strongest at the outskirts where the restoring pull from the home galaxy is weakest. It shows as a gentle bend of the luminous edge, one side a little higher, the other a little lower, with the centre still close to flat. Dust lanes follow the bend, and the faint gas layer flares, slightly expanding its thickness as random motions grow. Patterns in the rotating disk adjust as well. Spiral arms that were open with a certain pitch become a little tighter on the side that faces the approach and a little looser on the far side. The difference is modest at first, yet it can be traced by the distribution of bright knots where gas is denser. These knots are not yet numerous, but they outline the places where streaming motions compress the interstellar medium. Stars on nearly circular paths feel a small additional inward pull on the near side, and a small outward pull on the far side. Over many revolutions, these tiny nudges shift the guiding centres of their orbits, and create a barely visible lopsidedness in the starlight. Gas responds with both gravity and pressure. In lanes that already hold more material, the extra pull draws in new parcels from just outside the arms. When these parcels meet, their relative motions cause gentle shocks that raise the gas density. Cooling follows because denser gas radiates energy more efficiently. As it cools, it becomes easier to compress further, so the process reinforces itself. In a few places, small groups of young stars begin to appear, seen as blue clusters that shine through thin dust. Around them, pockets of glowing, ionized hydrogen form, where newborn stars bathe their surroundings in ultraviolet light. These pockets are small and scattered, and the overall disk remains largely unchanged, but the first visible signs of the encounter now sit along the inner edges of the spiral pattern. Farther out beyond the bright disk, the halo responds in a different way. The dark matter halo is a wide well of gravity that extends far beyond the stars. As the other halo draws near, the contours of the combined well skew toward the line joining the two centres. Very old stars in the halo move on extended orbits that now precess, slowly changing their orientations with respect to the approaching mass. The sum of many small changes gives the halo a faint stretch along the direction of the approach, even before any bright tidal tail becomes distinct. Satellite dwarf galaxies that once orbited in quiet loops feel the extra gradient across their paths. Some have their outer stars lifted into diffuse streams that trail behind them, while their cores continue on, now guided by the shifted field. Within the main disks, the central regions remain quiet in this early stage. The dense bulges hold stars on many inclined paths that average out disturbances, and the supermassive black holes at the centres stay dark and still with respect to the surrounding stars. Gas near the centres maintains pressure support against self-gravity, and shows only small changes in its distribution. The most notable difference is a slight increase in non-circular streaming within any faint bar that may already exist. Tidal torques can strengthen a weak bar by shifting angular momentum from inner to outer orbits, and once the bar strengthens, it can move gas inward along its leading edges. At this stage, the effect is gentle. Flows are slow and spread over large radii, and no sudden bright nucleus appears. If an observer could watch from a fixed vantage point not bound to either galaxy, the change would be a gradual increase in the apparent size of each system as seen from the other. The near edges look a shade brighter because more stars lie along that line of sight within the bent disk. Between the galaxies, a very faint bridge of diffuse light may begin to emerge, where streams from the outer parts overlap, though it remains subtle against the dark. The intergalactic gas remains too thin to offer much resistance, so there is no sharp bow wave, only a long, quiet overlapping of extended halos. The timing of all these signals is long when measured by human clocks. The outer halo leads the response, then the outskirts of the disk, then the inner disk, and finally the very central regions. The sequence reflects the freefall time at each density, shortest in the densest inner parts, and longest in the diffuse outer envelope. Yet the trigger comes from the outside, so the first visible deformations often show far from the centre. Warps and flares, asymmetries in the arms, slight offsets in the light distribution. and the first scattered patches of ionized gas together draw a plain picture of two large structures beginning to feel each other's presence. Tidal radii shift as the mutual pull grows. Material that once lay well inside the safe region becomes marginal, and in a few sectors of the outer disk the balance tips. Stars and gas lifted there do not immediately fly away. They move into long, slow arcs that trace the evolving field. Because stars are so widely spaced, they continue to pass without direct collisions. Their paths are set by the joint potential, rather than by encounters with one another. Gas clouds being compressible show the encounter more readily through mild shocks cooling and the birth of small groups of young stars. The overall brightness of each galaxy changes only by a modest amount, yet its shape now carries a memory of the other's pull. As the distance continues to shrink, the invisible envelopes overlap more deeply, and every part of each galaxy receives the message that a companion draws close. The message is always the same in form, a gradient in gravity that varies smoothly across space. The response is orderly because the timescales are long and because the motion is largely collisionless for stars. In this early approach, the scene remains calm when viewed as a whole. The disks rotate, the bulges glow, the halos stretch a little, the outer edges lean into a shallow curve, the gas marks slight lines of compression that thread the arms. Young clusters appear here and there like quiet sparks. Each sign is small, but together they show that two great systems now share one broad field and that their steady approach continues. As the two galaxies continue to close the distance between them, tidal forces begin to leave clearer marks on their structures. A tidal force is the difference in gravitational pull felt across an extended body, and in galaxies this difference is large enough to reshape the arrangement of stars and gas without breaking their overall coherence. On the side nearer to the partner, stars feel a stronger inward pull, while on the far side the pull is weaker. This imbalance stretches the disk along the line that connects the two centres. Because the outer regions are only loosely bound, they are the first to yield. Stars that once moved in nearly circular paths around their home galaxy are nudged outward on one side and inward on the other, bending the smooth disk into a form that begins to resemble an elongated oval. From certain angles, the outer edges now sweep outward in thin arcs, while the main body stays rounded and bright. These elongated features are the earlier stages of tidal tails. They are not single objects, but streams of stars that have been pulled from their former paths and now follow new orbits shaped by both galaxies at once. The streams trace the joint potential like ribbons of light that mark lines of force, and although they appear fragile, they remain coherent for long times, because stars within them move together with small relative speeds. The gas component responds more strongly. In the outskirts, gas that lay close to the tidal radius is stripped outward and pulled into bridges between the galaxies. These bridges are faint, but their presence can be detected by radio waves from neutral hydrogen atoms. Inside the disks, gas clouds are pressed into new lanes where tidal torques concentrate material. When gas is compressed, it radiates away, heat becomes denser and cools further, so the tendency is to collapse more strongly. This cycle produces conditions ripe for star formation. In regions where the compression is greatest, bright knots of newborn stars begin to appear. Their light is blue because young massive stars shine hotter and whiter than older cooler stars. Around them, envelopes of glowing, ionized gas form as the intense radiation strips electrons from hydrogen atoms. The growing patches of blue and pink mark places where the tidal forces are sculpting the next generation of stars. The spiral arms, which were patterns maintained by density waves, now distort under the new forces. One arm may extend farther outward, becoming stretched and thinned into a tail. Another may curl back, wrapped tighter than before. The balance that once gave the disk a nearly symmetric shape is lost, and the new form is lopsided. Dust lanes that trace the old arms now curve into sharp bends, giving the galaxy a twisted look. Despite the disruption, the overall rotation continues. Each star and each gas cloud still obeys the combined gravitational potential, so the motion is steady and continuous. The distortions do not come from sudden jolts, but from the persistent pull of the companion as it moves past. The bulges in the centres remain more stable because stars there orbit in many directions rather than in an orderly disk. Their mixed motions average out the differences in pull, so the bulge holds its round shape even while the disk stretches. The central black holes are still unaffected by direct interaction. They continue to sit at the centres of their local stellar swarms, moving only slowly with respect to the bulge around them. The large-scale shape of the galaxies, however, now shows clear evidence of tidal action. Streams extend outward for tens of thousands of light-years, some curving gracefully away, others pointing more directly toward the companion. Between the galaxies, faint bridges of stars and gas connect the two systems. These bridges are not permanent structures. They are temporary alignments of material flowing along distorted orbits. Yet they serve as evidence that matter has been lifted from the grasp of one galaxy and placed into paths controlled by both. The halos of dark matter interpenetrate during this stage. Because they hold most of the mass, the overlap makes the joint potential deeper and shifts its centre toward the space between the galaxies. As a result, the orbits of stars and gas in each galaxy adjust further. Outer stars may be captured by the partner, while others are sent into long excursions before returning. These exchanges contribute to the growth of the tidal tails and bridges. Dwarf companions in orbit around the larger galaxies are particularly vulnerable. Their outer layers are stripped and their shapes distorted sometimes, leaving long plumes that stretch across the group. Over long times, some dwarfs may lose so much material that only a dense core survives, while others are fully absorbed into the larger systems. From a distant vantage point, the scene is striking, but not violent in the sense of sudden impacts. The galaxies remain mostly intact, glowing strongly in their central regions. The distortions at the edges, the arcs of stars, and the knots of bright new clusters create a picture of graceful stretching rather than chaotic breaking. Because stars are so far apart, direct collisions remain extremely rare. The changes are governed by gravity acting on the collective distribution, not by encounters between individual stars. The tidal features also reveal information about the mass distribution in the galaxies. The length and curvature of tails depend on the depth of the potential well and on the speed of the encounter. A deep well holds stars more tightly, producing shorter and thicker tails, while a shallower well allows longer and thinner streams. By studying such structures in real galaxies, astronomers infer the extent of the dark matter halos and the timing of past encounters. In the ongoing approach, the two galaxies now swing past one another at their first close passage. The point of closest approach is brief compared to the whole orbit, but it is the time of strongest tides. Stars near the edges are flung outward, gas is compressed in broad arcs, and bridges are stretched across the gap. After this passage, the galaxies begin to move apart again, climbing toward epicenter of their mutual orbit. The tidal tails extend even farther as the systems recede, carrying stars to distances greater than before. Although the galaxies separate after this first encounter, they are not free of one another. Dynamical friction slows their motions, and the combined halo continues to drain energy from their orbit. As a result, they will not escape, but will fall back together for another pass. Each cycle brings stronger distortions, longer tails, more compressed gas, and more new stars. The first passage is the opening movement in a long interaction setting in motion, the gradual reshaping that will eventually merge the two systems into one. The evidence of tidal forces is now plane-warped disks, stretched arms, new star clusters, luminous bridges, faint but long streams, and a shared halo that binds both galaxies in its reach. Every feature grows from the same principle, the uneven pull of gravity across extended structures. The process is orderly, slow, and cumulative, and it continues as the galaxies trace their long paths under the steady rule of gravity. Gas clouds inside each galaxy now respond more strongly to the gravitational disturbances caused by the encounter. Unlike stars, which behave almost as collisionless particles and continue on their orbits with only gentle nudges, gas can compress heat, cool, and shock when flows intersect. This difference makes gas the most sensitive tracer of tidal interactions. In the outer disks, neutral hydrogen clouds are drawn outward into extended tails. Radio waves reveal these structures long before they appear bright in visible light. The tails can extend for hundreds of thousands of light years, and in some places the gas density grows high enough for new stars to form within them, creating faint remote star clusters strung like beads along the tails. Closer to the centres, gas is forced into narrow lanes where tidal torques and streaming motions push it together. When gas clouds meet, their motions are not perfectly aligned, so they collide gently and lose energy to shocks. The shocks compress the gas further, raising its density and lowering its temperature as the energy is radiated away. Dense, cool gas is prone to collapse under its own gravity, and this collapse leads to the birth of new stars. A sequence of events unfolds. Tidal forces distort orbits, orbits channel gas into lanes, lanes produce shocks, shocks create dense clouds, and clouds collapse into stars. The outcome is a rise in star formation rates across large portions of the galaxies. This process is often called a starburst. In some regions, the rate of star formation may increase 10 times compared with the earlier quiet disk. Starbursts are short in cosmic terms, lasting only tens of millions of years, but their imprint is vivid. Bright clusters of massive stars light up the distorted arms, and their ultraviolet radiation ionizes surrounding gas. Large glowing nebulae appear, marking the sites of recent collapse. These nebulae are irregular in shape because tidal streaming twists the lanes where stars are forming. The combined effect is a patchwork of blue young clusters and pink glowing clouds spread through the distorted disks. Within the centres, inflows of gas begin to grow. The gravitational torques from tidal distortions remove angular momentum from gas, allowing it to drift inward. Bars, which are elongated structures of stars and gas in the disk, become stronger under these conditions. Gas follows the bars along their leading edges and flows toward the nucleus. Their densities increase and new clusters of stars form close to the galactic centre. Some of this gas may eventually feed the supermassive black holes, though in this stage the inflow is still slow and spread over wide areas. The bulges remain luminous and relatively stable, but the new central clusters begin to alter the colour and brightness of the inner regions. As young stars form, they live fast and die young. Massive stars, many times the mass of the Sun, burn their fuel quickly and explode as supernovae after only a few million years. Each supernova releases energy that stirs the surrounding gas, heats it, and drives it outward in expanding shells. When many supernovae occur close together, their shells overlap and combine into powerful winds that blow out of the disks. These winds carry metal-enriched gas into the halos and even into the intergalactic medium. Thus, tidal interactions do not only trigger star formation, they also redistribute elements and energy far beyond the galaxies themselves. The pattern of gas flows is complex. Some gas is funneled inward to fuel central regions, while other gas is blown outward by feedback from new stars. The balance depends on details such as the mass of the galaxies, the speed of the encounter, and the density of the gas. In most cases, both processes occur at once, leading to a cycle of compression, starburst, feedback, and dispersal. The visual appearance of the galaxies changes markedly. Where once the disks showed orderly spiral arms, they now glow with scattered patches of bright blue light and luminous pink clouds. Long tidal tails arch outward, some dotted with new clusters. Bridges of faint starlight and gas connect the galaxies across the space between them. Dust lanes curve in sharp bends, tracing the distorted flows. The galaxies look chaotic to the eye, but every feature is a natural consequence of gravity acting on stars, gas, and dust. The stars, largely unperturbed in their motions, provide the smooth background light. The gas, sensitive and reactive, shows the encounter in sharp detail. Astronomers studying such systems in the sky can often tell at a glance whether an interaction has recently begun, is in full swing, or is nearing its end based on the presence of tidal features and bursts of star formation. The inflow of gas toward the centres is especially important for long-term evolution. As the galaxies continue to orbit and come closer again, the central inflows will grow stronger. The gas that piles up near the black holes may ignite bursts of radiation as it spirals inward, producing active galactic nuclei. Even before that stage, the build-up of dense central gas drives the formation of compact star clusters that change the inner structure. In the meantime, the outskirts continue to lengthen. Stars pulled into tails follow extended orbits that take them far from their original homes. Some tails may eventually fall back, raining stars onto the merged remnant, while others may become independent dwarf systems. The early generations of stars that form in these tails enrich the local gas, so that any returning material brings new elements with it. The ongoing star formation feeds on the gas reservoirs that were once stable in the disks. Over time, much of that gas is either consumed in stars or blown out into the halos. This depletion gradually reduces the fuel available for future star formation. Thus, the starburst phase, though intense, carries the seeds of a quieter future when the merged remnant will have less cold gas and will evolve more slowly. In these middle stages of an encounter, the role of gas is central. It records the gravitational disturbances in its flows and shocks. It responds by forming stars, it shapes the visible appearance with glowing nebulae, and it influences the long-term future by feeding both star clusters and black holes. Stars mark the outlines of tidal features, but gas reveals the processes that drive the transformation. The galaxies now shine with new brightness, not because of added mass, but because of the light from newly born stars ignited by the encounter. The quiet disks of earlier times are gone. In their place are distorted, glowing dynamic systems bound together by the steady pull of gravity and by the reactions of gas that cannot ignore compression. The story of their approach now moves into a stage defined less by geometry of arms and tails, and more by the birth of stars and the recycling of gas on grand scales. Young stars now begin to shine in great numbers as a direct response to the compression of gas clouds during the ongoing interaction. These stars are massive, bright and short-lived, so their appearance alters the light of the galaxies quickly. Clusters form where several large stars are born together, and their combined blue light spreads across the distorted disks. Some of these clusters contain thousands of stars, and their collective radiation ionizes nearby gas. Regions that were once dark now glow in irregular patterns of emission. The contrast with older populations becomes strong. Redder light from ancient stars still dominates the bulges and halos, but across the arms and tidal features the blue of newborn stars stands out. This mixture of colours reveals both the past and the present of each galaxy in a single view. The difference in lifetimes between stellar populations means that the new clusters will not last long. The most massive stars will end as supernovae after only a few million years. Their energy and heavy elements enrich the surrounding medium and help to shape the next round of star formation. The less massive stars in these clusters will live longer and may remain as bound groups for hundreds of millions of years, eventually dispersing into the background of the merged remnant. Some will survive as recognizable star clusters far into the future. Star formation triggered by tidal compression follows clear patterns. In the bridges that connect the galaxies, long chains of clusters appear like luminous beads. In the tails that sweep outward, clumps of gas collapse into small galaxies of their own. These tidal dwarf galaxies are built from material pulled out of the parent disks, and may remain as independent systems or fall back later. Within the main disks, dense lanes of gas along distorted arms host bright star-forming regions. The scale is vast, with many thousands of clusters forming across spans of tens of thousands of light-years. Each cluster adds its light to the overall appearance, so the galaxies glow more intensely than before. Along with light comes heat. Radiation from young stars heats the surrounding gas and raises its pressure. The pressure pushes back against further collapse, creating a cycle of star formation and regulation. In some places, gas continues to collapse despite the heating, while in others the feedback slows the process. Supernovae then add another layer, stirring the medium, blowing bubbles and driving winds. These winds can lift gas out of the disks and into the halos, where it may cool and rain back later, or escape entirely into intergalactic space. The result is a complex and self-regulating pattern. Star formation rises, feedback pushes back, gas is expelled, and some of it returns. The balance between these steps determines how many new stars form and how much gas is lost. The galaxies in this stage are noisy in terms of physical processes, yet their overall structure remains graceful when viewed from afar. Long tails arch outward, blue clusters sparkle in irregular rows, Glowing nebulae mark the youngest regions and faint bridges connect the two main bodies. It is a scene of steady creation under the guidance of gravity. Although the starbursts light up the galaxies, the rate of star formation cannot remain high forever. Gas reservoirs, though large, are finite. Each burst consumes a fraction of the supply and heats, or expels another fraction. Over tens of millions of years, the pace slows, but during this stage the increase is clear. The central regions begin to change as well. Bars strengthened by tidal torques continue to channel gas inward. Near the nuclei, dense concentrations of new stars appear, and the background glow of the bulges grows brighter and bluer. Some of the gas driven inward may settle into rotating disks around the central black holes. As material spirals closer, it heats through friction and releases radiation. At first, the flow is modest, but even a small fraction of the total gas can produce a noticeable increase in central brightness. These early signs may mark the beginning of an active nucleus. If inflows continue, the activity may rise, lighting the centers with radiation far beyond the combined starlight. Outside the central regions, the interaction drives further asymmetry. One galaxy may now appear stretched into a long form, while the other remains more compact. Their relative masses influence the outcome. The more massive system holds its structure more firmly, while the smaller one is more distorted. Yet both share in the creation of new stars because both supply gas to the overlapping region, and both feel the tidal forces that compress it. The geometry of the orbit determines where the most prominent features appear. A nearly head-on approach creates strong tails in opposite directions. A glancing passage produces curved streams and offset bridges. The angles of the disks at the time of the encounter also affect the shape of the tidal features. Some orientations produce symmetric tails, while others create one long tail and one short one. Despite these variations, the common element is the appearance of new star clusters across the distorted structures. Observations of interacting galaxies in the sky show these patterns clearly. Systems like the antennae galaxies display brilliant clusters strung along tails, bridges and central regions. Their light tells the same story described here: gas compressed by tides, stars born in clusters, feedback shaping the medium and light from newborn populations, transforming the appearance of the galaxies. Within the halos, old stars displaced by tides form faint streams that arc across the background. These streams are harder to see, but they trace the orbits of stars stripped from the disks. They contain no gas and no new stars, so they shine only with the dim light of old populations. Together with the bright clusters, they mark the full range of responses to the encounter. The stage defined by bursts of star formation is temporary but important. It builds many of the young populations that will inhabit the merged remnant. It redistributes gas spreads metals and sets the conditions for central activity. It also makes the galaxies unusually bright in blue light compared with normal spirals. If an observer looked only at their colours without seeing their shapes, the systems would stand out as unusually active. The galaxies remain bound by gravity, their paths still curving under the combined pull of their halos. After the first close passage, they move apart again, but not far enough to escape. The dynamical friction within their overlapping halos slows them, and they will soon fall back together for another approach. Each new passage will repeat the processes described here, compressing gas, creating clusters, and building tidal features. The visible signs of interaction will grow even stronger as time goes on. For now, the main marks are the glowing young clusters, the nebulae around them, the faint bridges and tails, and the steady transformation of gas into stars. This is the era when the galaxies look most alive with creation, their structures lit by stars that did not exist before the encounter began. It is a stage that bridges the quiet disks of the past and the eventual merged system of the future, and it unfolds slowly under the same rules of gravity that have shaped galaxies since their birth. Older stars that formed long before the encounter now begin to shift into new patterns as the galaxies continue their mutual dance. Unlike the gas which collides and compresses, stars pass through one another freely guided only by the changing gravitational field. Yet because that field is reshaped with every pass, their orbits are gently pulled into new paths. Over tens of millions of years, groups of stars that once traced neat circles in the disks are stretched into long arcs. Some of these arcs curve away from the main bodies and become visible as tidal streams. Others bend inward and form bridges of light between the galaxies. The result is a delicate tracery of stellar paths that register the history of the encounter without the bursts of activity that mark the gas. The stars most easily displaced are those in the outer parts of the disks. There the pull of the home galaxy is weaker, and the tidal force from the companion is stronger. Stars lifted from these regions follow orbits that take them far from their origins. Because they do not collide, they remain on coherent paths for long spans, forming narrow streams that arch gracefully through the halos. These streams can loop around the combined system, wrapping in long curves that trace the gravitational potential like ink in water. Their surface brightness is low compared with the main disks, but their extent is vast, and they carry with them the memory of the earlier galactic structures. In the halos themselves, old populations shift as well. Globular clusters that once orbited in quiet loops now feel the extra pull and are scattered into new trajectories. Some are captured by the companion halo and become satellites of the other galaxy. Others are set onto elongated orbits that carry them out to great distances before they fall back. The combined halo becomes a reservoir of displaced stars, clusters, and streams, a living record of the tidal interaction. Within the bulges, stars remain more stable. Their orbits are randomly oriented, so the tidal forces average out more effectively. The bulges retain their rounded shapes, though subtle shifts in density can occur as stars migrate slightly outward or inward. The centers remain luminous and dense, and they act as anchors around which the rest of the structures evolve. The contrast between the steady bulges and the distorted disks emphasizes the resilience of central concentrations compared with fragile outskirts. The formation of tidal tails from old stars is an especially striking outcome. These tails are drawn out on both sides of the interacting pair, often symmetric, but sometimes one longer than the other depending on the geometry. Each tail contains stars stripped from the outer disks, moving along paths dictated by the joint gravitational field. Because they contain only old stars, they shine with a reddish light lacking the blue of newborn clusters. Over time, they become diffuse as stars spread along their orbits, but they can remain visible for billions of years as faint extensions of the main systems. Their presence tells astronomers that an interaction has taken place even long after other signs have faded. The streams of displaced stars also form shells and ripples around the galaxies. When stars fall back after being lifted outward, they can pile up at certain distances where their orbits slow near upper center. These pile-ups appear as faint arcs concentric around the remnant. Such shells are commonly seen around elliptical galaxies, which are often the products of mergers. They represent the long-lasting memory of stellar displacements during interactions. As the galaxies continue their orbital motion, the displaced stars weave complex patterns. Some remain bound and will eventually be incorporated into the merged remnant. Others gain enough energy to escape entirely, becoming intergalactic wanderers. The balance between retention and escape depends on the masses of the galaxies, the speed of the encounter, and the depth of the combined halo. In most cases, a fraction of stars is lost, enriching the faint glow of intragroup light that fills galaxy clusters. The impact on the overall structure is gradual but profound. Disks lose their clean edges as stars are drawn into tails. The halos grow more populated with streams. The combined light distribution becomes more extended and irregular. The sense of order that defined the spiral arms diminishes, replaced by arcs and bridges that mark the tug of tides. The galaxies no longer look like isolated spirals, but like connected parts of a larger system in transition. The dynamical friction that continues to slow the orbital motion also affects the displaced stars. As the centers spiral closer, the stars in the tails and streams adjust their orbits to the shifting potential. Some tails fall back and wrap around the remnant, while others are flung farther out. The redistribution is ongoing, with each cycle of approach and recession adding new layers of displaced populations. From a distance, the process appears calm. Stars flow into new paths without colliding, and their collective light shifts smoothly into new forms. Up close, the changes are immense in scale spanning tens or hundreds of thousands of light years. The simplicity of the governing force gravity ensures that despite the apparent chaos, the motions are ordered and predictable. Old stars are not silent witnesses. Their distribution carries valuable information about the mass and shape of the dark matter halos. By mapping the streams and tails, astronomers can infer the depth of the potential and the history of the encounter. In simulations, the patterns of displaced stars match observed systems, closely confirming that the physical principles outlined here explain the shapes seen in the night sky. The transition of stars from neat disks into long arcs and bridges illustrates the difference between stability and change in galaxies. For billions of years, stars can orbit quietly, but a single encounter is enough to transform their arrangement permanently. The encounter does not erase the stars, but it redistributes them into new forms that will endure. When the merger is complete, many of these old stars will form the extended envelopes of the new galaxy, a broad and faint halo that surrounds the brighter core. For now, they stream outward, tracing the invisible shape of the combined gravitational field. They carry the past into the future, spread across space by the tides that now dominate the evolution of the pair. The sight of these displaced stars, if it could be viewed directly, would be one of vast streams of light arcing between and beyond the galaxy's silent but eloquent signs of the encounter. The disks are no longer intact, the arms no longer symmetric, and the outskirts no longer quiet. Instead, they are drawn into elegant curves that will take hundreds of millions of years to settle, and they show in detail how gravity sculpts matter on galactic scales. At the heart of each galaxy lies a supermassive black hole, a compact concentration of mass millions to billions of times greater than the Sun. During the early stages of an encounter, these black holes remain largely untouched, still anchored in their bulges and orbiting slowly within the joint gravitational field of the merging system. Yet as the galaxies draw nearer and their cores begin to interact more directly, the influence of these central objects becomes more significant. Stars in the bulges respond to the changing potential by redistributing themselves around both centers. Some stars are flung outward into the halo while others sink closer to the middle. The two bulges move around each other in tightening orbits, carrying their black holes along like hidden anchors. The paths of these massive objects are set by the balance between gravity pulling them together and dynamical friction with surrounding stars and dark matter slowing their motions. Over tens of millions of years, the separation decreases and the black holes draw ever closer to one another. Gas inflows triggered by the tidal distortions continue to feed the nuclear regions. As gas is channeled inward through bars and tidal torques, it piles up in dense central disks. The rotation of these disks carries angular momentum that must be shed for the gas to fall further inward. Shocks, turbulence, and self-gravity within the disks allow this to happen. When enough gas reaches the innermost regions, it begins to spiral into the black holes. As it does so, the gas heats to extreme temperatures and radiates strongly across the electromagnetic spectrum. At this stage, the galactic centers may flare into active galactic nuclei with radiation far brighter than all the surrounding stars combined. The form this activity takes depends on the rate of inflow. Modest rates produce luminous but compact nuclei. Larger inflows may create broad outflows or jets of material launched at near-light speed from the regions around the black holes. These jets pierce through the surrounding gas and carry energy out into the halos. Although such events seem violent, they are simply the result of gas obeying gravity and releasing energy as it falls. The black holes themselves do not change visibly. Their presence is revealed only by the light from infalling matter. At the same time, the mutual orbit of the black holes tightens as they sink deeper into the combined bulge. This happens because each black hole pulls on stars as it moves, creating a wake behind it. The wake carries away energy and momentum, and the black hole loses orbital speed as a result. The process known as dynamical friction is slow but relentless. Eventually, the two black holes form a bound binary system, orbiting around their common center of mass within the merged bulge. The scale of their separation shrinks from thousands of light years to hundreds, then to tens. During this long approach, the surrounding stars are continually stirred. Some are flung onto new orbits, or even ejected from the galaxy entirely. The cumulative effect carves out a lower density core around the binary, a phenomenon that astronomers can see in the light profiles of some galaxies today. Gas near the binary continues to be drawn inward. The interaction between gas disks and the binary system may accelerate the shrinking of the orbit. At the same time, feedback from accretion onto the black holes injects energy into the central regions, stirring turbulence and heating gas. This feedback can limit the inflow, creating a cycle of feeding and expulsion that regulates how rapidly the black holes grow. The presence of two black holes alters the symmetry of the gravitational potential near the center. Stars that wander too close can be captured into chaotic orbits slingshotted by the binary, or consumed if they pass within the tidal radius of either black hole. These rare events add to the slow redistribution of stars in the core. The fate of the binary depends on how efficiently it can lose energy and angular momentum. Stellar scattering can shrink the orbit to a point, but once the separation is reduced to less than a parsec, further progress requires new mechanisms. Gas interactions may continue to assist, and at the smallest scales, the emission of gravitational waves becomes the dominant factor. Gravitational waves are ripples in space-time produced by accelerating masses. For a binary of supermassive black holes, the waves carry away orbital energy, steadily causing the orbit to shrink further. The timescales for this process can be millions to billions of years, depending on conditions. Eventually, however, the black holes will merge, forming a single more massive object and releasing an immense burst of gravitational radiation. During the present stage of the interaction, the two black holes are still separate but moving closer. Their surrounding bulges are distorted yet still distinct. Each remains surrounded by its local population of stars, and both continue to accrete gas at varying rates. If one galaxy is richer in gas than the other, its nucleus may shine more strongly. From a distance, the system may appear as a pair of luminous centers within distorted disks connected by bridges and tails. Observers would note the unusual brightness of the nuclei, the irregular star-forming regions, and the streams of stars extending far into space. The influence of the black holes also extends indirectly to the larger system. The energy they release through accretion can drive winds that push gas out of the central regions, limiting further star formation near the core. In extreme cases, this feedback can alter the evolution of the galaxy by removing a large fraction of the cold gas that would otherwise have formed stars. This regulation is a key reason why many large elliptical galaxies, which are thought to be merger remnants, have little star formation today. The eventual merger of the black holes is far in the future relative to the current stage. For now, the key point is that both remain bound to their host bulges and are spiraling slowly toward one another under the steady influence of dynamical friction. Their presence ensures that the final remnant of the galactic merger will contain a single, even larger, supermassive black hole at its center. Until that time, they continue their quiet approach, unseen directly, but traced by the motions of stars and the radiation from gas that falls into their grasp. The galaxies around them shift and distort, but these compact objects remain steady anchors, guiding the central evolution of the system with their immense but invisible gravity. As the galaxies continue their mutual orbit, the dense centers that contain the bulges and black holes draw nearer step by step. The outer disks have already been reshaped into tails, bridges, and arcs, but the inner regions are only now beginning to respond in a stronger way. Stars in the bulges feel the steady tug of the companion bulge, and the two concentrations move in spirals around each other, while dynamical friction slows them down. With every passage, the distance between them decreases. The process is not fast on human timescales, but on galactic scales it is decisive. Over hundreds of millions of years, the two cores drift closer, exchanging orbital energy with the surrounding halos and streams. Each approach stirs the stars and scatters some outward, while the central density of the bulges grows as material flows inward. The two bright centers circle each other within the same envelope, their paths curving like dancers bound by a tether that shortens with time. The stars that inhabit these bulges do not collide, but their orbits are altered by the combined pull. Some stars are shifted onto elongated paths that carry them outward into the halo. Others sink closer to the middle, building up the density around the cores. The motions are complex but governed by simple rules: conservation of energy, conservation of angular momentum, and the constant pull of gravity. The outcome is a slow contraction of the orbit of the two bulges. Gas continues to play a vital role. Bars and tidal torques that were triggered earlier still drive inflows toward the central regions. Streams of cold gas spiral into the inner kiloparsecs, feeding bursts of star formation near the nuclei. Compact star clusters form, some of them so dense that they may survive as bound systems long after the merger. Radiation and winds from these clusters stir the gas, while supernovae inject further energy into the central medium. This cycle builds up the light of the inner regions and alters their colours toward the blue of young stars. At the same time, inflowing gas reaches the vicinity of the black holes, where it heats and radiates as it spirals inward. In some cases, both nuclei may shine at once as active galactic nuclei, producing a pair of luminous centres separated by only a few thousand light-years. These dual nuclei are clear signs of an advanced stage of merging. Observers would see distorted galaxies with two bright cores glowing against a background of tidal features and young clusters. The gravity of the dual cores reshapes the potential well of the system. Stars that orbit within this central region no longer circle a single centre, but move under the influence of two. Some stars are pulled into chaotic orbits and may be ejected at high speeds, leaving the galaxy entirely. These ejections contribute to populations of hypervelocity stars that wander between galaxies. Other stars settle into new orbits around the combined mass of the two bulges, helping to stabilize the inner structure. The overlapping of the bulges begins to erase their separate identities. The density peaks move closer until they start to merge into a single, brighter core. The surrounding stars' gas and dust flow into this new central concentration. At the same time, the overall shapes of the galaxies change. The disks, already stretched and warped, lose their distinct outlines. Spiral patterns are disrupted beyond recognition. What remains is a pair of central bodies enveloped by stream shells and tails, all slowly blending into one extended structure. The relative motion of the cores is damped by dynamical friction, with the background of stars and dark matter. Each time they pass, they transfer energy to the surrounding particles, which are set on new orbits farther from the centre. The cores lose orbital energy and sink deeper into the potential well. The path is not a simple straight line. It is a decaying spiral that winds inward as momentum is drained away. Gas near the centres accelerates the process. Dense disks of molecular gas form around each nucleus, and as these disks interact, they create torques that rob the orbiting cores of angular momentum. Some gas falls directly into the central regions, feeding the black holes and increasing the brightness of the nuclei. Other gas is flung outward, carrying away momentum and shaping the flows. The result is a more rapid inward drift than would occur with stars alone. The merging of the cores alters the balance of star formation. The intense compression near the centre creates superstar clusters, which are groups containing millions of stars bound together in compact volumes. These clusters shine brightly and may remain as long-lived globular clusters in the remnant. Their presence adds to the richness of the stellar population in the merged galaxy. The visible appearance during this stage is striking. Two bright cores sit close together within a cloud of stars and gas surrounded by long tails that curve into space. The light from new clusters sparkles across the system while the faint glow of displaced old stars outlines the extended streams. Dust lanes cut through the central regions, obscuring parts of the nuclei and creating irregular patches of darkness. The overall impression is one of complexity and transformation, a system no longer composed of two distinct galaxies, but not yet a single settled remnant. The process of cores drawing nearer is central to the eventual merger. Until the black holes and bulges unite, the galaxies cannot be said to have fully combined. The gradual contraction of the orbit, the inflow of gas, the bursts of star formation, and the stirring of stars all lead toward this outcome. Each step follows directly from the laws of motion and gravity. Nothing happens abruptly, but over long spans the cumulative effect is profound. The future of the system is already clear. The two cores will spiral together, their stars will merge into a single bulge, their black holes will form a binary, and then coalesce, and the disks that once defined them will be gone. For now, the stage is set by the sight of dual centers within one distorted body shining brightly amid a field of arcs and streams. This is the moment when the galaxies are closest to still being two, yet are already becoming one. A transition written in the light of their stars and the flow of their gas, all governed by the patient but irresistible pull of gravity. When the galaxies finally overlap deeply enough, the distinction between their stellar populations begins to blur. The disks that once carried graceful spiral arms are stretched, folded and scattered until they no longer resemble their original forms. Stars from both systems mix together within a shared envelope, moving under the influence of the combined gravitational potential. The luminous structures that arise at this stage are complex, with shells, arcs and streams intertwining around the merging cores. To an observer at a distance, the two galaxies no longer appear as separate systems. Instead, they present as a single tangled mass of starlight threaded with dust lanes and glowing patches of gas where new stars are forming. The overlapping produces a merger of stellar populations. Old stars from each disk and bulge join to form an extended halo, while younger populations remain concentrated in knots and clusters along the tidal features. The colour of the system reflects this mixture, with the reddish glow of ancient stars blending with the bluish light of newborn clusters. Dust obscures some regions, scattering and reddening the starlight and creating irregular patches across the system. Gas dynamics are central to the appearance of the merger. Streams of gas continue to fall inward along tidal lanes, fueling central starbursts, and in some cases active galactic nuclei. Collisions between gas clouds produce shocks that compress the medium, and dense filaments radiate strongly as they cool. The result is an ongoing cycle of collapsed star formation feedback and dispersal that operates across many scales. Some of the newly formed clusters lie in the tidal tails far from the centres. These clusters may evolve into small independent galaxies or return later to become part of the remnant. Others are born close to the nuclei where they contribute to the brightening of the central regions. The balance between inflow and feedback determines how long the starburst phase continues. Supernovae from massive young stars inject energy into the gas-driving winds that can carry material out of the system entirely. The interaction of these winds within falling streams creates turbulence and irregular structures. Dust carried by the winds adds to the obscuration in the central zones. Despite the turbulence, the overall gravitational framework is smooth. Stars follow ordered orbits within the deepening potential well. The chaos is only apparent when looking at the gas and the visible features it produces. The stars themselves, though redistributed, maintain a collisionless order. Their streams and shells trace graceful curves set by gravity. The bulges of the two galaxies now overlap closely. Their stars intermingle, and the light profile in the central regions begins to take on a single peak rather than two. The black holes at the very centres orbit within a common bulge, continuing their slow spiral inward. Around them, dense nuclear star clusters form glowing brightly in the inner few hundred parsecs. The light from these regions is intense, fed by the constant formation of massive stars and by the radiation from gas falling toward the black holes. The structure of the merged body takes on a more rounded shape. The thin disks are gone, replaced by a spheroidal distribution of stars. The tidal tails still extend outward, but they are now clearly external features rather than parts of ordered disks. As time passes, some of these tails will fall back, wrapping around the central body to form shells and ripples. Others will disperse into intergalactic space, leaving faint streams of stars behind. The overall appearance is closer to that of an elliptical galaxy than to a spiral. The transformation is not instantaneous, but emerges gradually as the central concentration grows and the outer features fade. Dynamical friction continues to play its role. Every time the cores orbit within the merged envelope, they transfer energy to the surrounding stars and dark matter, which move on to wider orbits. This process shrinks the orbit of the cores and accelerates their union. The transfer of energy also puffs up the distribution of stars, making the central body more extended and rounder than before. The resulting profile matches what is commonly observed in elliptical galaxies, with a smooth light distribution and little sign of a disk. Star formation in the central regions eventually consumes much of the available gas. The bursts that once lit the tidal features and nuclei gradually fade as fuel is depleted or expelled by winds. As the starburst winds down, the colours of the system shift again toward the red dominated by older populations. Only scattered clusters of young stars remain as evidence of the earlier burst. Dust settles or is dispersed, and the central light emerges more clearly. The system as a whole grows quieter. During the full merger phase, the visual impression is one of overlap and mixture. The two galaxies are no longer distinct, yet they have not yet settled into a single smooth remnant. The tails, streams, and bridges remain obvious, but the central body is unified. The dual cores are now separated by only a small distance, and their black holes are approaching the final stage of their orbital decay. The complexity of the scene reflects the variety of processes at work: tidal stretching of stars, compression, and collapse of gas bursts of star formation feedback from supernovae and black holes, and the long-range influence of gravity shaping the overall form. Each process leaves a mark, but all are woven together by the steady rules of motion. Observers studying such systems in the universe can reconstruct their histories by reading these marks. Tales point to the geometry of encounters. Starbursts reveal the flow of gas shells, and streams trace the redistribution of stars, and luminous nuclei signal the activity of central black holes. Together, these signs tell the story of galaxies in transition systems, reshaped by the pull of one another into forms that differ profoundly from their origins. The merger of starscapes is both a blending and a transformation. It preserves the matter of the original galaxies while rearranging it into new structures. The outcome will be a larger, more massive and more spheroidal system, but the path to that outcome is written in the overlapping light and gas of the present stage. It is not destruction, but reorganization carried out on scales so vast that the passage of time itself seems to stretch with the flow of matter. What was once two spirals is now becoming one body, a galaxy in the making, formed not by sudden collapse but by the patient embrace of gravity, drawing systems together and mixing them into unity. To the eye, the overlapping galaxies now resemble a single immense structure. Yet within that structure, the motions of countless stars remain ordered by gravity rather than chaotic collisions. The sense of violent collision is an illusion created by the stretched shapes and glowing patches of new stars. In truth, direct encounters between stars are nearly impossible because of the vast distances between them. Even when galaxies pass fully through one another, the average separation of stars in a disk is several light-years far larger than their diameters. Each star continues on a smooth path determined by the evolving gravitational potential of the whole system. This apparent paradox, where the scene looks turbulent but the motions are calm, is one of the keys to understanding galactic interactions. The stars behave like particles in a collisionless fluid moving past one another without contact. What changes is their collective arrangement. Gravity alters the orbits of large groups at once, stretching them into tails, bending them into bridges, or redistributing them into a smoother spheroid. The overall picture is of calm, continuous motion that appears violent only when viewed in light. Gas tells a different story because gas clouds are extended, compressible, and subject to shocks. When gas flows intersect, they collide, compress, and release energy. The bright star-forming regions are born from these collisions, yet even here the processes unfold over millions of years, not seconds. Shock waves travel slowly compared with the scale of the galaxies, and the collapse of gas into stars is measured in tens of millions of years. The impression of sudden bursts comes from the brightness of massive young stars rather than from the speed of formation. On human timescales, the transformation of two galaxies into one is inconceivably slow. Every tidal tail, every arc of displaced stars, every glowing cluster takes tens or hundreds of millions of years to appear. From the perspective of the universe, however, this timescale is moderate. Galaxies live for billions of years, and mergers are recurring events in their histories. The slow pace ensures that the changes are orderly, and the conservation laws that govern motion guarantee that the process is comprehensible and predictable. Because direct collisions between stars are so rare, the fate of stellar systems such as planetary systems is more secure than appearances suggest. A star like the Sun embedded in a galactic disk may feel its orbit shift during a merger, but the chance of another star passing close enough to disrupt its planets is vanishingly small. Planetary orbits may be nudged by the changing galactic potential, yet most systems remain intact. The main changes are to the orbits of the stars around the galactic centre, not to the smaller scale orbits within each system. This difference underscores the distinction between appearance and reality in galactic collisions. The visual impression is of chaos and destruction, but the physical reality is one of calm orbital adjustments spread across immense spans of time. The galaxies evolve through gentle reshaping rather than through catastrophic impacts. The dynamics of the dark matter halos reinforce this calmness. The halos contain most of the mass and provide the deep gravitational wells in which stars and gas move. When halos interpenetrate, their combined potential changes smoothly. The stars respond to this smooth potential, not to each other directly. This is why the paths remain ordered. It is as if the galaxies were fluids pouring into one another, guided by invisible basins. The smoothness of the halos ensures that even in deep overlap, the stars follow predictable motions. Astronomers have tested these ideas with detailed computer simulations. In these models, each star is represented by a particle that moves under gravity. When two model galaxies are set on a collision course, the result is a graceful unfolding of tails, bridges, and streams, not a destructive clash. The simulations reproduce the features seen in real systems with remarkable accuracy, confirming that the appearance of violence is deceptive. The importance of this lies not only in understanding the present merger, but also in comprehending the broader history of galaxies. Many elliptical galaxies observed today show evidence of past mergers. Their smooth light profiles, extended halos, and occasional shells or streams all point to histories shaped by interactions. The absence of disks in these galaxies is not the result of destruction, but of redistribution. Stars that once traced ordered spirals were stirred into orbits of many orientations, producing the round shapes of ellipticals. Gas that once formed neat lanes was consumed or expelled, leaving behind systems dominated by older stars. The stage now unfolding, where galaxies overlap but stars rarely collide, illustrates how such transformations occur. Another subtle point concerns energy. The orbital energy of the two galaxies must go somewhere as their centres spiral inward. That energy is transferred to the stars and dark matter in the form of higher velocity dispersions. In effect, the random motions of stars increase. This is why the final remnant has a rounder shape and no disk. The ordered rotation of the disks is converted into the random motions of the spheroid. The laws of conservation ensure that the energy is not lost, but redistributed across the many components. From a distance, the current stage of the merger may look like a violent crash. Dust lanes cross luminous cores, tails stream outward, and patches of blue light mark intense starbursts. Yet beneath this appearance is the calm order of gravity. Stars glide past each other without contact, guided only by the evolving potential. Gas clouds compress slowly into new stars. Black holes spiral closer at a measured pace. Nothing happens abruptly, yet over hundreds of millions of years the system is transformed completely. The apparent violence is therefore an illusion born of scale. For creatures whose lives are measured in decades, a process that takes hundreds of millions of years seems explosive. In reality, it is a slow choreography of matter. Gravity shapes the paths, conservation laws set the outcomes, and time provides the canvas on which the picture unfolds. Understanding this distinction allows one to see galactic mergers not as catastrophes, but as phases in a natural cycle. Galaxies grow by merging. Their shapes, their star populations, and their central black holes are all outcomes of this steady process. The current stage shows the principle clearly. Even in deep overlap, stars do not collide, but the system as a whole changes shape. The seeming contradiction is resolved by the immense scale of space between stars and by the smoothness of the gravitational potential. The lesson is that what looks chaotic is in fact orderly when measured against the governing laws. The merger continues steady and calm, though to the eye it may seem fierce. The long spiral of orbital decay gradually brings the two galactic centres into close proximity, and as they approach their final coalescence, the system takes on a new shape. The once prominent disks are no longer recognisable, for their ordered rotation has been converted into the random motions of a spheroid. The tidal tails still extend outward, but they are thinning as stars disperse, and as some of the material begins to fall back. The central body is brighter and rounder, with a light profile that resembles that of an elliptical galaxy rather than a spiral. This transformation is a direct result of energy transfer. The orbital energy of the galaxies has been given to the stars' dark matter and gas, raising their velocity dispersions and spreading them into more varied orbits. The ordered rotation that defined the spirals has been erased. Stars now follow paths oriented in many directions, filling the volume of the remnant evenly. The central concentration is dense, with the light dominated by the merged bulges and by the stars that formed during the starburst phase. The remnant shows a smooth distribution of starlight punctuated by dust lanes and knots where gas remains. The supermassive black holes, now bound in a tight binary, continue to spiral inward. Their influence is strongest in the innermost regions, where they stir stars and eject some at high speeds. The central light profile shows signs of being hollowed, a signature of stars flung out by the slingshot effect of the binary. Meanwhile, gas near the nuclei feeds the black holes and creates bursts of radiation. For a time, the remnant may host a luminous active nucleus, shining across great distances. Jets or outflows may carry energy into the halo, further regulating the availability of cold gas. As star formation slows because gas is depleted or expelled, the remnant reddens in colour. The bright blue light of massive newborn stars fades quickly as those stars die in supernovae. What remains is the steadier red glow of older, longer-lived stars. The shift in colour marks the transition from an active starburst system to a more quiescent remnant. Dust clears as winds disperse it, and the central light becomes less patchy. The shape of the galaxy grows more regular. The remnants of tidal tails can still be seen in faint arcs around the central body. These shells and streams represent stars that were pulled outward during the merger and are now falling back on elongated orbits. At apocenter, where their orbits slow, they pile up briefly, creating brighter arcs that look like ripples. Over time, these features spread out and fade, but for billions of years they remain as fossil evidence of the merger. The gas that remains in the outer regions is diffuse and heated. Some of it has been driven out by supernova winds and by energy released from accretion onto the black holes. Some remains bound to the halo, forming a hot atmosphere that may cool only slowly. Without abundant cold gas, the remnant forms new stars at only a low rate. The transformation is nearly complete. Two spiral galaxies that once rotated with ordered arms have become one large elliptical or lenticular galaxy, dominated by old stars and with only residual traces of its gas-rich past. The black holes, though not yet merged, are close, and will eventually coalesce, sending out a burst of gravitational waves. Until that time, they remain hidden in the core, their presence revealed by the activity of surrounding gas, or by the motions of nearby stars. From a broader perspective, the remnant joins the population of massive galaxies that inhabit groups and clusters. It carries within it the memory of its origins in the form of faint shells, star clusters, and the chemical signatures of past starbursts. The distribution of heavy elements in its stars reflects the bursts of formation triggered by the merger. The extended halo contains streams of stars from both progenitors now blending into one envelope. Globular clusters from each galaxy orbit within the new system, their numbers increased by the clusters formed during the starburst. The shape and light distribution of the remnant reveal the essential processes that occurred. The erasure of disks shows the role of energy transfer. The central concentration shows the effect of inflows and bulge merger. The faint outer features show the tidal stripping and redistribution of stars. The lack of abundant cold gas shows the feedback of starbursts and black holes. Each part of the remnant carries the imprint of a mechanism. Together they form the outcome of a long and steady transformation. To an observer who compares the present remnant with the spirals that existed before, the difference is profound. Yet the matter is the same. The star's gas and dark matter that once defined two galaxies have been rearranged into a new form. Nothing was destroyed in the sense of being lost, but everything was reshaped. The process required only the patient work of gravity, acting on extended systems over hundreds of millions of years. This is the essence of a galactic merger, not a sudden impact, but a slow reorganization of matter. The remnant will continue to evolve, settling further into equilibrium. The shells will disperse, the hot gas will cool or escape, the black holes will merge, and the light distribution will grow smoother. Over billions of years, the galaxy will take its place among the population of massive ellipticals distinguished by its size, its faint halo of tidal debris, and the massive black hole at its center. Its history will be legible to those who look closely, but its present form will be that of a stable system, shaped by the lasting influence of one great event. The final coalescence of the centers, the smoothing of the light and the fading of the tidal features together mark the end of the merging phase. The two galaxies are no longer visible as separate entities. What remains is one galaxy, larger, rounder, and older, in appearance carrying forward the stars of both progenitors into a common future. The new galaxy that emerges from the merger no longer has the thin, rotating disk of its spiral ancestors. Instead, it takes on a rounder and smoother form, a spheroid of stars with little sign of spiral arms or ordered lanes of dust. The stars that once moved together in neat circular orbits have been stirred into paths that point in many directions, filling the volume evenly. The ordered motion of rotation has been converted into random motions in all orientations. The overall shape is that of an elliptical galaxy, with a smooth light distribution that falls off gradually with distance from the center. This transformation is the natural outcome of the merging process. As the galaxies interpenetrated, the orbital energy of their centers was transferred to the stars and dark matter. That energy gave the stars higher random speeds and dispersed them into broader orbits. The result is a system without the thin, flat shape of a disk. The spheroid shines with the combined light of billions of stars, most of them old and reddish, but it also contains younger populations created during the starbursts of the merger. These younger stars are scattered through the body and in the shells and streams left over from the tidal tails. Over time they will age and redden, blending with the background population. The light of the new galaxy is therefore dominated by older stars, but for now it still carries traces of the bright blue clusters born during the merger. The gas content of the remnant is much reduced. Much of the cold gas was consumed in forming new stars. Another large fraction was heated and expelled by winds from supernovae and by feedback from the central black holes. The remaining gas is hot and diffuse, forming a halo around the galaxy that radiates mainly in X-rays. Without abundant cold gas, new star formation slows to a low rate. The remnant is on a path toward quiescence with only scattered pockets of activity. This decline in star formation is one of the marks of an elliptical galaxy. The shape of the remnant reflects the details of the merger. If the two spirals were of similar mass, the outcome is a large, nearly spherical elliptical with smooth light. If one was much larger, the remnant may be more elongated or may retain some trace of a disk, becoming what is called a lenticular galaxy. In either case, the defining feature is the loss of clear spiral structure and the dominance of random motions. The stars that once traced arms are now dispersed into a rounded distribution. Observers studying such remnants in the sky see smooth profiles of light that fit simple mathematical laws, with brightness falling as a function of radius in predictable ways. These profiles confirm that the stars have redistributed into equilibrium under gravity. The central regions of the remnant are marked by the presence of the black holes. The binary black hole continues to spiral inward, though at this stage their separation is small compared with the overall size of the galaxy. Eventually, gravitational waves will carry away the final orbital energy and bring them together into one more massive black hole. The merger will send a burst of gravitational radiation across the cosmos, though it will be invisible in light. Afterward, the core of the remnant will contain a single enormous black hole, a concentration of mass that anchors the galaxy. Around it, nuclear star clusters remain as dense knots of light relics of the inflows that accompanied the merger. The outskirts of the remnant still carry the memory of the interaction. Faint arcs, ripples, and shells outline the paths of stars flung outward and now falling back. These features are low in surface brightness, but can persist for billions of years. They are signatures that astronomers use to identify galaxies that have undergone mergers. Some globular clusters orbit far from the center remnants of the original halos. Others were formed in the starburst and now orbit as new globulars. The system as a whole is richer in clusters than its progenitors, reflecting both inheritance and creation. The remnant also shines with intragroup light the diffuse glow of stars that were lost entirely from the main body during the merger and now float between galaxies in the surrounding group. These stars are not bound to any one system, but trace the larger gravitational potential of the group. Their presence confirms that some fraction of stellar mass is always dispersed in such events. The chemical composition of the stars in the remnant records the past. Old stars from the original spirals carry the metallicities of their disks and bulges. New stars formed during the merger carry the enriched material of the starbursts. Together they create a broad distribution of element abundances. Astronomers studying the spectra of elliptical galaxies can read this record, finding evidence of bursts of star formation in their chemical fingerprints. The present appearance of the remnant is therefore both simple and complex. Simple in its overall shape, which is smooth and rounded. Complex in its details, with faint outer features, multiple populations of stars and traces of dust and gas. The galaxy stands as a new system distinct from its progenitors, shaped by the merger into a form that will endure. Over time, the galaxy will settle further. The tails will disperse into the halo, the shells will fade, and the young stars will age. The light will become smoother and redder. The system will join the population of ellipticals that dominate the cores of galaxy clusters. Its growth may continue through new mergers, for the process of galactic assembly never truly ends. But the great transformation has already occurred. 2 spirals have become one spheroid. The transformation illustrates the cycle of galaxy evolution. Spirals rich in gas form stars steadily until interactions drive them together. The merger consumes and expels gas triggers starbursts and transforms ordered rotation into random motions. The result is an elliptical galaxy, older, redder, and more massive. This cycle is repeated across the universe, building the population of galaxies we see today. The remnant is the living product of that cycle, a new galaxy born not from collapse alone, but from the union of 2 long-lived systems. It carries the past into the future, its stars, clusters, and black hole bearing witness to the processes that shaped it. What was once 2 galaxies is now one shining quietly in the dark, its form set by the steady hand of gravity. Deep within the merged galaxy, the binary of supermassive black holes continues its inward drift. At separations of only a few light years, their mutual orbit is tight enough that their motion is dominated by each other, rather than by the surrounding stars. Yet even at this distance, they still carry vast amounts of orbital energy that must be lost before coalescence. The transfer of energy takes several forms. Stars that pass close to the binary can be flung outward at high speed, carrying away momentum and shrinking the orbit. This process creates what astronomers call a loss cone, a region of phase space depleted of stars that once orbited near the black holes. Replenishing the loss cone requires new stars to wander inward through random encounters, and this continual scattering sustains the slow tightening of the binary. Some of the stars ejected by this process achieve velocity sufficient to escape the galaxy entirely. They become hypervelocity stars travelling alone through intergalactic space. Each ejection robs the binary of energy and brings the 2 black holes closer together. Gas also plays a role. If dense gas disks form around the binary, their gravitational torques can remove angular momentum from the black holes. Streams of gas falling inward may interact with the binary, exchanging momentum and driving the orbit smaller. At the same time, accretion of gas continues to feed the black holes, producing radiation that can rival or exceed the combined starlight of the galaxy. Outflows from these active galactic nuclei can heat and expel gas from the central regions, limiting further star formation. The cycle of feeding and feedback shapes the final stages of the merger as much as the gravitational interactions themselves. As the separation shrinks to less than a parsec, gravitational waves begin to dominate. These ripples in space-time carry energy away at the speed of light, causing the orbit to decay more rapidly. The frequency and strength of the waves increase as the orbit tightens. For millions of years, the binary may emit gravitational waves too faint to detect. But in the final moments, the radiation becomes strong enough to ripple across the cosmos. When the black holes finally merge, they form a single, more massive black hole and release an enormous burst of gravitational energy. The galaxy itself scarcely notices, for the energy is carried away in a form that interacts only weakly with matter. The surrounding stars continue their motions as though nothing had happened, but the space-time around the core quivers briefly with the merging waves. The final black hole may recoil slightly from the asymmetric emission of radiation, shifting its position within the core before settling again. The new central black hole anchors the remnant as the deepest point in its potential well. Its mass is greater than either progenitor's, reflecting both the merger and the gas it has consumed. The motions of stars near the center reveal its presence, for their speeds increase with proximity to the core. Over time, the influence of the black hole extends across the inner regions, shaping the density profile of the stars and regulating the inflows of any remaining gas. The merger of black holes is not only the end of one process, but the beginning of another. The coalescence seeds a central object that will influence the galaxy for the rest of its life. Feedback from accretion episodes will continue to heat and stir gas. The depth of the gravitational well will define the motions of stars and clusters. The link between the mass of the black hole and the velocity dispersion of the bulge observed in galaxies across the universe reflects the intertwined growth that mergers like this produce. The visible galaxy also continues to evolve after the black hole merger. The central starbursts fade as fuel runs out. The blue clusters age their massive stars, dying and leaving behind fainter populations of red dwarfs and remnants. The dust is dispersed by winds and radiation, clearing the view of the nucleus. The once irregular body smooths into a more regular spheroid, with only faint shells and streams left as memory. The galaxy now resembles a typical elliptical, massive, red and quiet. Yet the record of its merger remains written in its structure. Faint arcs in the halo trace the fallback of stars from tidal tails. A rich population of globular clusters orbits the core, many formed during the bursts of star formation. The central light profile may show a core scoured by the binary black holes. These signs allow astronomers to identify the galaxy as a product of a past merger long after the event itself has ended. The surrounding environment also bears the imprint of the merger. Some stars were ejected entirely and drift as intragroup light. Gas expelled by winds enriches the intergalactic medium with heavy elements forged in stars. The mass of the new galaxy alters the gravitational field of its group, changing the orbits of neighbouring dwarfs. The influence of a single merger thus extends beyond the galaxies involved, affecting their environment on larger scales. The gravitational wave burst from the black hole merger travels outward without attenuation, carrying the signature of the event to the distant universe. If there are observers with instruments sensitive to such waves, they can detect the coalescence directly. The pattern of the waves encodes the masses and spins of the black holes and confirms the role of mergers in growing these massive objects. In this way, the final stage of a galactic merger is not silent but speaks through space-time itself. The timescales for all of these processes are immense. The orbital decay of black holes may take hundreds of millions of years. The emission of gravitational waves grows strong only in the final minutes, yet those minutes are the culmination of an epoch-long spiral. The fading of starbursts and the aging of clusters unfold over billions of years. The final settling of the remnant into equilibrium is measured in cosmic time. Yet each step is continuous, governed by the unchanging laws of motion and gravity. The merger of black holes is therefore both a dramatic and a calm event. dramatic in the scale of energy released, calm in the effect on the surrounding stars. It is the fitting end to the long union of galaxies, the point at which even their deepest anchors combine. The galaxy that remains is larger, rounder and quieter than either progenitor, a stable system that carries forward the legacy of two long-lived spirals into one enduring elliptical. The system that once consisted of two spirals has now become a single galaxy in equilibrium. Its overall shape is that of a spheroid, smooth in outline with stars distributed in orbits that fill space evenly. The thin, rotating disks are gone, their ordered motion erased during the merger. The light of the remnant is dominated by older stars, reddish in colour, while the younger populations formed during the starburst still shine as blue clusters but are already aging. Over time, these clusters will fade, leaving behind long-lived stars that blend into the background. The remnant is therefore on a path toward becoming steadily redder and more quiescent. The central black hole, now the merged product of the binary, anchors the system. Its gravity shapes the orbits of stars in the inner regions and regulates the inflows of gas. During episodes of accretion, it shines as an active galactic nucleus releasing energy that heats and stirs the surrounding medium. Even after the fuel declines, its presence remains dominant, an invisible weight at the centre of the galaxy. The bulge that surrounds it is bright and dense, with stars moving at high speeds in random directions. The relation between the mass of the black hole and the velocity dispersion of these stars is a lasting imprint of their shared growth. The outskirts of the remnant still preserve memories of the merger. Faint shells, arcs and ripples trace the fallback of stars that were flung outward during the tidal interactions. Streams loop through the halo, some wrapping around the system in long curves. These features are faint, but with careful observation they can be seen as fossil records of the past. Globular clusters from both progenitor galaxies orbit in the halo, joined by new clusters formed in the starburst. The system is rich in such clusters which serve as traces of its history. Some stars were lost entirely ejected during the merger by interactions with the binary black hole, or by the tides of the overlapping halos. They drift through the intra-group medium as part of the diffuse light that fills galaxy clusters. Gas that was expelled during starbursts and active phases has enriched the surrounding space with heavy elements. The merger has therefore altered not only the galaxies themselves, but also their environment. The remnant as a whole is now stable. Its light distribution follows smooth mathematical laws, with brightness declining predictably with distance from the centre. The random motions of its stars provide pressure support against gravity, maintaining equilibrium. The hot gas halo glows faintly in X-rays, a reservoir of material that cools only slowly. Without large reserves of cold gas, new star formation is minimal. The galaxy has entered a phase of slow evolution, with changes measured over billions of years. To astronomers, such remnants appear as giant ellipticals. They are found in abundance in the centres of galaxy clusters where mergers are frequent. Their smooth profiles, rich cluster systems, faint tidal debris and massive central black holes all point to histories of mergers. The transformation of spirals into ellipticals is one of the main processes of galaxy evolution, and the system described here is a clear example. The cycle is complete. Two rotating disks have combined into one spheroid. The gas has been consumed or expelled. The stars have been redistributed. The black holes have merged. What remains is a single galaxy, larger and more massive than its predecessors, carrying within it the memory of its origin. The timescales involved are vast, but the outcome is enduring. This galaxy will persist for billions of years, slowly fading as its stars age, slowly accreting new material from its surroundings, and perhaps one day merging again with another system. The universe is filled with such processes repeated endlessly across time. Each merger reshapes galaxies, builds new structures, and grows central black holes. Each remnant carries the signature of its past in its shape, its stars, and its clusters. Observing these remnants allows astronomers to reconstruct histories that span billions of years. The final form is calm, quiet, and stable, a contrast to the apparent turmoil of the merging stage. The illusion of violence has given way to the reality of order. The new galaxy shines steadily in the darkness, its structure fixed by gravity. It's light. The sum of countless stars born in different epochs, its centre bound by a black hole of enormous mass. It is no longer two but one, a galaxy remade by the slow and patient work of gravity.